समुद्रवसने देवी पर्वतस्तनमण्डले विष्णुपत्न्यै नमस्तुभ्यं पादस्पर्शं क्षमस्व मे. Those who dare to fly don't care to leave their footprints behind. Welcome to FVS. Very good morning to all of you.
Good morning, sir.
Yeah, hope you had a good Dashara. How many of you were able to attend the Vaibhav sessions, at least one of them? Okay, good. I see a few hands going up. That's good. Quite a few have attended the at least one Vaibhav session. So we concluded all the panel discussions yesterday, and many of the takeaways from that will actually be utilized in enhancing the self-reliance capabilities of India going forward through collaborative modes. And that is precisely why I was also talking about collaborations and the importance of that in the previous class as well. Not only between you, but between whoever can enhance the capabilities of nations or the globe in a mutually beneficial manner. So those collaborations should always be looked for. So that was the purpose, and so it's just the beginning that we have made to identify the kind of people involved in various aerospace technologies and the gaps that are there in the research and also the technology development in the country, so that we can see where whose prowess can go and how they can collaborate with each other to take this forward. So this was an exercise just to make those identification of both the topics as well as the people. Now that exercise has been completed, we are going to be taking this forward in terms of actually coming up with specific proposals in order to accelerate our movement towards self-reliance in these technologies, not only for the Indian population but also for the exports in the future. So thanks for many of you for attending these Vaibhav sessions because you are the future, and I see a lot of prospect going forward that you will be able to contribute to the kind of foundation that we are laying out right now. So we'll go ahead with today's class and share my screen. Hope you're able to see my slide.
Yes, sir.
Okay, excellent. So now we talked about in the previous class the load-based classification. So we'll just revisit that before getting on to the major topic for today, which is material selection. So we said that the components can be classified as one-dimensional or two-dimensional predominantly. Amongst the one-dimensional components are the axial force bearing bars and columns, depending upon whether they are in tension or compression respectively. Those which bear torque and therefore called as shafts, again thin-walled, and the bending moment, which is typically taken by beams, which again are thin-walled, typically I sections, etc. Examples being spars. The fourth being the panels, which could be predominantly the cover skin of the fuselage and or the aerodynamic surfaces, as well as the webs of the spars. So these are the two-dimensional surfaces, very good at taking shear loads coming from both torsion as well as the transverse shear from the lift and the drag. So then we said that in order to enhance the efficiencies, we have to model three-dimensional structures as either 1D or 2D, taking advantage of the smallness of either one dimension compared to the other two, or two of the dimensions compared to the other one. So when we do that, obviously accuracy suffers, but if we do that properly, this dimensional reduction, which is what our efforts in this course will be towards, the drop in accuracy would be negligible, but the increase in efficiency would be typically 10 to 100 times, which is going to save a lot of cost, both in terms of the money as well as, more importantly, the amount of human resources spent in terms of number of hours, the time that is taken in order to take a product from the design stage all the way to the market. So this being the situation was the reason why I had put up that quick quiz a few days back. I'm glad that many of you have responded. I think there were 36 responses at the time I collected this data. And out of them, I think 35, vast majority, have selected column under compression, which is quite obvious, because if there is a column which is under a compressive load, then obviously there is going to be compression, and that's where you study the conventional classical buckling models. And for example, for a simply supported beam, you arrive at pi squared EI by L squared as the buckling load. So that was quite obvious. So you see about 35 people having said that, almost 100% of the class. That was kind of a giveaway, because compression is there both in the question as well as the answer. And but if you actually look at the other categories, it's nice to see there's a quite good distribution over there, which was a pleasant surprise for me, because you've been giving a lot of thought to this. And so if you look at the second most popular answer was, of course, this is a multiple choice question, so the same people could have answered many of these. So the second most popular answer was 24 people saying that the beam under concentrated transverse force. Yes, so when you have a beam like this and you're applying a concentrated transverse force over here, this is predominantly going to be bending, but at the same time this transverse force is going to cause a transverse shear, and that transverse shear in turn can cause buckling, but at the same time the bending also causes compression, which can cause the buckling. The transverse shear part, let me come to a little later, but the predominant part is because the transverse load causes bending, which is experienced by both tension on the top and the compression in the bottom, and therefore the bottom portion, if the load is downwards, that is. So then the bottom portion is having compression, so that it can undergo a local buckling. So it's not buckling like in the first case of the column under compression, where the entire structure is buckling. Here it is a local buckling which is happening in the bottom side, because the top side is under tension, that cannot buckle, it's still stable, but the bottom portion, which is under compression, can actually undergo buckling, what we call as local buckling, or in the case of the skin, it could be a wrinkling. So very similar to the wrinkles that we get in the skin when we get old, or the wrinkles in the cloths. So similarly, there is a wrinkling effect that is happening in the bottom. So we'll get into these terminologies when we study elastic stability in a little more detail. But that is the main possibility. But I just gave a hint that transverse shear can cause it too. So let's keep that aside for now. Now coming to the next most popular was the beam in pure bending. Very good. So pure bending basically means that the bending moment is the only thing which is there. There's no shear force. So there's a for example, in a cantilever beam, there is a tip moment which is there applied, and therefore there's a constant bending moment distribution along the length of the beam, and there's no shear force. So this bending moment once again can cause the compression the same way like we described in the previous example. Next, the most popular, so therefore the compressive portions, for example, if it's an I section, let us say, in the case of an aircraft wing which is undergoing lift, and therefore it's bending upwards. When it's bending upwards, it's the top portion which is going to be under compression. So the, for example, the spar which is there, which could be an I section, let us say, the top flange of the spar is going to undergo compression, and there is a possibility that it could buckle if there is sufficient load, which means that a very large amount of lift, which means the load factor is very large, for example in a maneuver, etc. And in such situations there is a possibility that can undergo buckling if not designed properly. In any case, the skin itself, the top skin, will anyway undergo local buckling, and that is allowed for. So the next most popular one I see is almost equal. You see that beam under distributed transverse force, which is what actually the lift and drag distribution in an actual aircraft is. It's a distributed transverse force in the vertical direction for the lift and in the horizontal direction for the drag if you're having a horizontal flight, a cruise flight, let us say. So, or more specifically, the lift is in the direction which is perpendicular to the airflow velocity, and the drag is in the direction which is along the direction of the airflow velocity. So in either case, you have a distributed force which is going to be causing a bending moment, and that bending moment in turn is going to be reacted by a cross section, partly by tension, partly by compression, and those regions under compression can undergo local buckling. So this is an important distinction that we are drawing between global buckling on the one hand and the local buckling on the other hand. Almost all of you would have studied global buckling, at least in a cursory fashion, but local buckling is something which is very common in aerospace structures, and so it's a unique thing that we let go and operate in the post-buckling regime. That's why I just wanted to bring this aspect at the point when we are introducing these different classifications of components based on the loads. Next, the one that you said is the panel in pure shear. This is what kind of pleasantly surprised me. This, as well as the shaft in torsion, which received 12 votes, because both are right. So, in fact, the correct answer was all of the above were actually right. I said one or more answers could be right, but actually all of them were right. If you sufficiently increase the load, there is a possibility that all of these can actually go towards buckling or instability, either global, as in this case, or local in the other cases. So let's revisit this and see why, for example, a panel in pure shear, or let's say shaft in torsion, can actually undergo buckling. It's kind of, let me probably share my other screen. Are you able to see my other screen now? Yeah. Okay, so what happens, for example, when there is, let's say, a panel. Okay, so let's say, can you see this, what I'm drawing?
Sir, I'm not able to see, sir.
You're not able to see?
No, sir.
No? Okay. Yeah, now you should be able to see, I guess. Yeah?
Yes, sir.
Okay, very good.
Yes.
So now let's see, there is this panel, okay? So suppose I have a panel over here, let's say in the X direction is this way, Y direction is this way. So you would have on this face, which is the negative X face, you would have a shear stress like this, a shear stress over here, a shear stress over here. Okay, so we call this as tau on the X surface in the Y direction, tau on the y surface in the x direction, etc. So this is also tau yx and tau xy, right? Now, so this is a panel in pure shear, okay? So there's only shear loads which are applied to this particular panel. So I'm quite happy to see many of you saying that this can undergo compression and therefore a possibility of buckling. Can any one of you who answered this unmute yourself and let me know why you said this?
Sir, this is me, Transverse. I said that because pure shear stress tau is there, and on the plane 45 degree and 135 degree, the plane stresses will be there, sigma 1 and sigma 2 value, and both these values will be equal to tau only.
Excellent.
So that is why I said that buckling will happen.
Excellent. Yeah, that's the right answer for this question. So for some of you who may not have clearly understood what Samanvai very well explained, what he's saying is that yes, in this particular coordinate system xy, it looks like there is only shear. But stresses can be transformed. Stress is a property at a particular point, and it is a directional property, not only like a vector, but it's a second rank tensor. It has the direction in which it is operating as well as the plane on which it is operating. So when we change the plane at which it is operating, because this is, though we are drawing the whole panel here and showing the load, the stress is actually at a particular point. So let's say this particular point, which is the origin over here, and at that point we are actually looking at the stress. This is an infinitesimal element of that panel, let us say, of length dx or delta x and dy delta y in the x and y directions respectively. Now if we actually look at an angle at 45 degrees and 135 degrees, as very well pointed out by Samanvai, you are basically looking at something like this. So a panel like this, which is basically at 45 degrees to the x-axis over here. So parallel to that, you're parallel and perpendicular to that, you're taking another infinitesimal element over there. So now if you resolve these stresses, what actually happens is you actually have a tensile load over here, and you have a compressive load over here. So that is basically what is actually happening. You can see that in terms of the resolution, if you look at what is happening at this particular corner, for example, you can see that's basically pulling it out. So in that sense is where this particular thing comes out. So this is what is happening over here. On the other hand, if you look at this particular corner over here, it's basically pushing in. So that's basically what is happening out here. And some of you, most of you, I guess, would have studied the Mohr Circle as well. So the Mohr Circle basically for this particular example of a pure shear becomes quite simple. So the Mohr Circle is basically a plot between the shear stress in different planes at a particular point and the normal stress, right? And for this case of the pure shear, all it means is that there is only a stress over here and a stress over here, which basically means that the Mohr circle is going to be something like this. So which is centered at the origin, and this is, if this value of tau xy or tau yx is, let's say, tau naught. So then the radius of this circle is tau naught, so it cuts the top vertical axis at tau naught, the bottom at tau naught as well. And then you actually have, because it's a circle, the the points at which it cuts the x-axis is also at tau naught. So as rightly pointed out by Samanvai, the value of the normal stress that you have here is also sigma naught. So this sigma naught is not an issue because it's tensile, it's not going to cause buckling. But on the other hand, this is, that's sigma naught equal to tau naught. Okay, sigma naught equal to tau naught, and this sigma naught equal to tau naught on this face as well as this one is the one which is going to cause compression in this particular direction, and that compression, if the tau naught is increased to substantially, that can cause a compression and that can cause the buckling. So is this clear? Are there any doubts from any students on this possibility of a panel in pure shear undergoing buckling? Okay, so that's good. So there are no questions related to that. Let's move on. And so the other example that we had was, of course, in the case of the torsion of the shaft. So let's say you have so you're applying a torque. So just recognize that whenever we put a double arrow head, it basically means a moment, which could be either a bending moment or a torque. So in this case, it's a torque applied on this particular shaft, which is let's say torque T, which if you introduce, let's say, an x1 axis over here and x2 and x3, which are in the cross section of the shaft. So we call this T as m subscript 1. That's a moment about the x1 axis. Similarly, if there is a bending moment about the x2 axis, for example, if this was part of a wing, let us say, then there will be a bending moment about the x2 axis caused by the lift, which we will call as m2, and the one about x3, which we will call as m3. Right now, let's say this is only under torque, because that was the question there, shaft under torsion. Okay, so it will be resisted, of course, in this end by the same value of torque for the equilibrium's sake. So this is under torsion. Now, what actually happens under torsion is basically the way it is resisted at any particular cross section is in the terms in terms of the shear stresses. So because of this torque which is coming outwards in this particular direction, you're going to have that being resisted in the opposite direction by shear stresses, which are going to be generated in this particular way. So now, because this is acting on the one surface and it's acting in a direction which is along the circumferential direction, which is theta. So we can introduce an r theta z coordinate over here, the cylindrical coordinate system. So in that sense, going by our usual convention of having the first subscript as the plane on which the stress acts, and the second subscript being the direction of the stress itself. Okay, so in that sense, this is a tau 1 theta, because 1 being along the x1 direction. If you use an r theta z coordinate, you would say tau z theta. Okay, so now the same, whether it's in polar coordinates or in Cartesian coordinates, you would also have a complementary stress which is coming on the perpendicular surface. So there would be on the surface of the that's along the length of the shaft, you would have the shear stresses as well, which are complementary to this. Okay, so it is not on the outer surface, but on the walls of that shaft, if it's a thin walled shaft, or even if it's a solid shaft through the entire cross section. And these will start becoming smaller and smaller as you go closer to the center of the shaft, and at the exact center there will be no shear stress at all. So this fact that you have this shear stress, again you can take one panel on this surface over here, or actually in the interior, and that interior surface will have a very similar stress state like what we described for the panel. That is, basically you have a situation like this where you have a stress situation which could be like this. Okay, so therefore even though it looks like it's under pure shear because of the torsion, you would still have at 45 degrees to that, you would still have the compression which is basically coming, and therefore if the torque T is substantially increased, then it is possible that this particular element can actually undergo compression. And this is very common, especially when you have thin walled shafts. It's not so much of an issue when you have solid shafts. So in thin walled shafts there can be what is known as torsional buckling. Okay, even in solid shafts, if it's possible, if the design is such that the material doesn't fail before that, usually the material would fail in that case, but if the material doesn't fail, there is a possibility that you could have a torsional buckling in that case also. But there is also a possibility, because there are combined loads which are acting in most structures all the time, you would see that the sometimes a flexural buckling, that is a buckling due to the bending, or the buckling due to a compressive load might occur prior to the torsional buckling, because the torsional load has still not reached that level. So it's the combined case that we have to look at, and we should see which of these is the dominant one leading towards buckling. We will of course study buckling in a little more detail later, but I just wanted to give you a flavor of this right now in a qualitative sense, only because you should not start bifurcating or demarcating these components that we talked about in a very singular sense, because there is so much more to it than what actually meets the eye. We say, let's say the beam under bending is undergoing bending, but there is a possibility that it can undergo compression and therefore buckling as well. Same way with the shaft in torsion as well. So I hope this is clear. Are there any questions or doubts on this?
Hello, sir.
Yes.
Sir, I have one doubt regarding this pure bending case.
Okay.
Sir, in pure bending case, one part above this neutral axis will be in compression, and other part of the beam will be under tension.
Right.
So the part under compression is prone to buckling, right? But sir, at the same time, we have the other half of this beam which is under tension.
Yeah.
And the moment that other part which is under compression wants to buckle, the other part under tension will resist this buckling.
True. True.
So, in a way, it is acting like a transverse stiffeners kind of thing. The one other half to the other. So that was the reason that I thought that buckling will not happen in this case of pure bending and.
Let me illustrate that for you. What you're saying is right, that the portion under tension will actually try to resist that, and it will probably delay the buckling. Okay, so suppose that was not attached at all, it would have buckled much earlier. But the fact that it is attached is going to cause the buckling to occur. So if you take a section like this, and this is under a tip moment, let us say m0. Okay. Now at a particular, so once again let's introduce the coordinate system. x1, x2, that is perpendicular to the plane of what I'm writing on, and this is x3. Okay, so now if you take the x2 x3 plane, it could be a box beam like what we talked about earlier, with the let's say the front spar over here and the rear spar over here, and the top portion, this element is undergoing compression, and this is undergoing tension. okay, because of the direction in which we have drawn this moment m naught, right? Now the bottom is going to be under tension, the top is going to be under compression. Now what we are saying is that under this pure bending, you can have the top portion, because it's under compression, susceptible to the buckling. If the m naught is increased quite a bit, then it can lead to buckling of that top element, right? Now what you're saying is that these other elements that are joined to it, let's say the web of the front spar, the web of the rear spar, and this bottom skin, which are all under partly the front spar and rear spar partly under tension, but the bottom entirely under tension, are going to resist that. But what we are talking about, the distinction that we made in the buckling, is basically twofold. One is the global buckling that you're all familiar with. That is the classical Euler buckling formula for a simply supported column of pi squared EI by L squared. That is the critical load for that. So that is valid only for the global buckling if the entire structure is under compression. But what we are now talking about, without going into the equations for that, is basically the local buckling that is happening. Yes, what you're saying is right. If I remove this element and keep it separately like this, it will buckle at a much lower load. But the fact that it is joined to these three elements, and of course many stringers, etc., is going to delay that buckling, but it's not going to preclude it in general. Okay, so there is still a possibility towards it reaching buckling. So wherever there is a possibility towards compression, even locally, even though the rest of the structure might be undergoing tension, there is a possibility that if the load is substantially increased and the structural design is not good enough to take care of that, it can definitely lead to buckling. So there is a possibility there. Whether it will really happen or not, there are many different variables which will determine that. Okay, so is that clear?
Yes, I got it.
Okay, good. Very interestingly, I saw one more answer. Somebody introduced another option and said other. Would that person let me know what exactly they meant by saying other? Because I think that is probably the only, I'm just guessing, because there were 36 respondents and 35 of them said column under compression, apart from many other possibilities, but one of them said the other. Would you like to explain what you meant by other there? Okay, that's fine if you don't want to talk right now. So let's go back to what I was discussing.
Sir, I have one doubt regarding pure bending. So, sir, isn't it the case where that beam will fail in bending before the buckling?
Yes, yeah, you are right. So it is in fact very much a possibility. It all depends upon the design. So how you have actually designed the whole structure. But for example, if you're talking of an I-section beam, which are very thin flange on the top, so then it is possible that the buckling might happen before. So it's all a question of how you're designing the structure, what materials are there, what is the geometry of the overall geometry of the beam, as well as the geometry of the individual components of the beam. For an I-section, the flange geometry, the web geometry, etc. So all of these will determine which happens first. So but theoretically any of these possibilities are there, and whichever you have to check for all of them, and whichever is the minimum, that will happen first. And even after that happens, it might still be able to bear the load unless it is a severe material failure, and therefore you might still be able to handle the additional load. But now that member which has failed, for example, the top flange is under compression, let us say, because of the lift, and that has failed, the rest of the spar will still be able to handle the load. So there's a kind of a redistribution that would happen. So you would have to actually look at case by case basis. The reason why I'm mentioning that possibility is that you have to check for this possibility also. You never know, depending on the design, whether this can occur before or after. But if it is well designed, what you're saying is right, that in most cases, because if that is the primary load that is going to happen on that particular structure, you design it for that and make sure that that is what will dictate its failure also at a sufficiently large level. Is that clear?
Yes, sir.
Okay. Let me see. Are you able to see my slides again? Or not?
No, sir.
Okay. Let me see what's happening. Now?
Yes, sir.
Okay. Good.
Yes, sir.
Okay. Now we are going to into the material selection. The materials can be of choice, can be either the metal like a traditional design, metallic alloy. When I say traditional design, it's almost like 40, 50 years since composites have been used in aircraft structures. So people continue to use this terminology traditional, but even many composites have become traditional in usage. But whatever the material choice is, you will have to answer these questions of why you are using that particular material, what specific material are you using, where are you using it, and how will you be using it, including the manufacturing and etc. But the fact is that no single material will be sufficient for designing typical aircraft, especially a large aircraft. Very small aircrafts, maybe you can do with a single type of material. But as you have a larger aircraft flying at faster speeds, there are various components in it, and some components might benefit by some material choices more than some others. And therefore, you will have to mix and match these materials. So you typically have a hybrid material design. Almost all the aircrafts. So which material goes where and why? These are important questions to answer, which we will try to do. So though the title here says composites, this is something that is going to be eventually valid for all types of material selection, as we shall shortly see in today's class itself. Okay, so what do these questions typically mean, and what is the brief answer to it? Though a few classes will actually be taken to answer each of these questions, we will look at in terms of a brief answer why, for example, why you use composites. Obviously, there are certain merits with respect to the other choices, typical choices you have, like aluminum alloys, steels, or titanium alloys, typically the metallic constructions. And in the past, also you have the natural composite, which is the wood or cloth, these kinds of combinations as well. So obviously, when you're choosing, let's say, a synthetic composite, carbon fiber epoxy or glass fiber epoxy over one of those earlier used materials, obviously it should have a certain merits. So what are those merits? So those merits basically should be in terms of their structural performance, or it could be in terms of the cost which is involved. Okay, so you might be it might be a cost constrained design where you are really trying to minimize the cost, and therefore you might want to see that whether that cost is actually dictating the material choice. So, and that cost in turn will actually be broken up into three parts. It is basically the initial material cost, that you have to buy that material to use that material in a particular location. The second is basically the manufacturing cost, because the material comes in a certain form, factor, and you have to shape it to the structure that you want to have it in, and probably cure it as well. If it's a wet composite pre-preg, for example, fabric, let us say, so then you have to, or if it's a metal that you are getting, it could be a sheet metal that you have to cut and shape it according to the particular location that you want to use it, let's say in the cover skin of a fuselage or a wing. So how much money, time, and human resources are spent towards manufacturing. So that is a cost which is involved as well. So it's not just the initial material cost. Then a third, often overlooked cost by many aerospace design engineers, unfortunately, especially as students, is the maintenance cost. So you have bought the material, you have made the aircraft with those materials that you have bought. Now, what about the running cost? So there is, depending upon the choice of the material, there can be variation in the material costs as well. So, for example, if you have a material like steel, which is prone to corrosion and it's operating in corrosive environments, you'll have to probably do a coating, and if that coating wears off, you'll have to recoat it. So something like that. So you'll have to look at those aspects of the cost as well. So always remember, it's not just the structural performance which dictates the choice of the material, but the economics as well. And the economics is always broken up into these three: of the initial material cost, the manufacturing costs, because some materials are easy to work with compared to the other. The manufacturing costs might be lesser for them. So, and then the third one, which is, and the manufacturing also of course includes not only the individual component shaping, but sizing and shaping, but also joining it with the other components which may or may not be made out of the same material. Then how do you actually bring in those joints? So all of that comes under the manufacturing cost, and eventually the maintenance cost in terms of taking care of that material's performance being within the acceptable levels. It might be at a very high level soon after manufacturing, but slowly degrades because of the fatigue loads that are there, and various other things that can happen to the aircraft structure, like impacts, etc. That might be repaired if necessary. Then what is the repaired structure, how it's going to behave, etc. So all of these are to be accounted for in the overall life cycle cost of a aircraft structure. So irrespective of all that, whether it is from the structural performance point of view or the cost point of view, or structural performance per unit cost, if you can arrive at some kind of a specific design criteria like that, then that is what actually dictates your choice of a particular material. And it should, the material that you choose should have certain merits compared to all the other potential choices that you have. And the third thing, of course, is again often overlooked by us engineers, is the geopolitical situations. So in terms of the availability of those materials, some materials might be available to a particular nation, some may not be, in terms of the resources that nation itself generates, or the other nations, how friendly they are in terms of transferring that technology, those materials, etc. So for example, if you have the silicon carbide fibers of aerospace grade, this is manufactured in just a few countries, and even though those are friendly countries like the US and US, France and Japan, all three very friendly countries to India, we are still not able to get this silicon carbide fibers from them for especially for large scale applications, because these are dictated by companies over there, in particular GE in the US, Snecma in France, and Nippon in Japan. So these three together make the silicon carbide fibers, which are basically very useful for high temperature applications, especially in aircraft engines, etc. So these geopolitical considerations have to be taken into account. So silicon carbide might be a great choice for a particular component that you're making within the engine, but if you're not able, and it might be of in terms of an overall life cycle cost, it might be a substantial advantage as well. So there are merits there, but then you have the constraint of the availability of those materials at a particular location that you are working from. So that is the Y aspect, basically focused on merits subject to certain constraints like costs and the availability. The second question that we need to answer in a material selection is, especially in the case of the composite, is that it's not a single material that you're choosing. It's at least two materials. There can be more if it's additional reinforcements are there, a hybrid ply, for example. But predominantly just at least these two choices of which fiber you're going to use and which matrix you're going to use, and what is the percentage of each in terms of the volume fractions that you're going to use. So this is again a choice that has to be made. So within the composite, you have to make that choice even after you decide to go for a composite. Then again, even within the fibers, let's say you say a carbon fiber, there are so many different varieties of carbon fiber, some which offer much higher stiffness, some which offer much higher strength, but not as high stiffness as the high stiffness carbon fibers. So certain locations which are dictated more by the dimensional stability, etc., for example, a space antenna application, etc., you might want to go for the high stiffness material choice. Whereas something else, you might go for the high strength choice if it is especially going to be loaded severely, a primary structure which is loaded very severely. So again, the failure levels will be different under tension and compression. So the choice that you have for the top cover skin and the top stringers of a wing might be very different from what you have for the bottom stiffeners and which is the stringers or longerons and the bottom skin, cover skin. So you would obviously choose, because the predominant load is the lift, though on the ground it is going to be bending down under self weight of the wing. That is not a critical situation. It's what is critical is the lift distribution, especially under higher load factors. So then you know that the top is under compression, so the stringers and the cover skin of the at the top will be designed based on materials which can take much larger compression over there, whereas at the bottom that is not as big a problem, and therefore you would look for something which is going to take much more strength in the tensile direction, right? So the next question that is asked is where you put the typical materials. You have a certain choice of materials, so which location you want to use which material, and at a single location how you stack them up. For example, if it's a hybrid construction, where you put which material. So I in one of the earlier classes I give you an example of a helicopter rotor blade which had the root, that is where the rotor blade is attached to the hub of the rotor. That particular location is usually thicker and usually have a hybrid construction over there. So you would see that there is a hybrid construction of glass epoxy with a carbon fiber. So where you use the carbon fiber, should you use it sandwich it in between the glass fibers, or you should do it the other way around? So all these choices will depend upon what kind of loads are there, why you are in particular using carbon fiber there, and so what is its primary purpose, whether to take the bending loads or the shear loads. And if it's the shear loads, you put it in between. If it's the bending loads that you predominantly want to take, you put it on the outer, because that's where the maximum bending stresses would be. So these are choices to be made not only from component to component which material you're using, but within a component particular location where you're using, depending upon the loads that are coming. So the application determines which material goes where. And finally, how you go about doing that, that is what most of this course will be about. So this why, what, and where will kind of set the stage for that how. Because then once we have decided this is the material which is going to a particular location, this is going to be its size and shape, then we need to analyze it or design it in a more detailed sense, refine it, optimize it, etc. For all of which we need to understand the mechanics of that material as well as the mechanics of the structure. By structure we mean a combination of material and geometry, which means a particular size and a shape for that component along with that choice of material. How are you going to analyze that? What is the stress which will occur there, strain occurring there at each point, which means a distribution, a field is what you're talking about based on the loads that are occurring over there, and therefore what are the displacements that are going to happen. So all of these things are under the gamut of mechanics, not just these but more than that, but broadly that is where it starts from. Okay, now let's look at this Y composites in a little more detail. So the material selection, as I said, is an important part of structural design. The other being the geometry design. Okay, so the geometry selection rather. The geometry both in terms of the size and the shape. Okay, so overall shapes again for many structures might be given from the aerodynamics, but the internal shapes and sizing are the prerogative of the structural engineer. The second aspect is that because material selection is an important part, the primary, though we talked about cost, etc., we'll not go into so much of detail in this course because these are beyond the scope of this course. But as choices, you would definitely need to look at that economics and geopolitics. Now let's restrict ourselves to the structural performance. From a structural performance point of view, there are certain physical properties, many physical properties for any given material. But which of those physical properties are of significance for a particular application? Certain things in a certain location, some properties may not be of much significance at all. Like for example, let's say in the case of an aircraft wing, let's say the property of the optical transmissibility of light in the sense of the opaqueness or transparency may not be of much significance there, whereas the strength and stiffness would be. So there are various physical properties coming from various physics aspects, but the predominant one you're going to be looking at is the strength, stiffness, and the density, because weight is critical in an aerospace application. So the three choices which were there almost as the predominant choices until, let's say, the early 70s of the previous century, 1970. So were the aluminum alloys, which were kind of winning over the rest by a large margin. But nonetheless, for higher temperature applications, you needed titanium, and for higher strength or stiffness applications, you needed steel. So these were the three choices which were predominant and still continue to be, even in the latest aircrafts like Boeing 787, Dreamliner, or the Airbus A350, which we talked about, which had as much as 50% by weight and 70% by volume of composites. You still have the rest being mostly made out of these metals. There are a few other combinations as well, ceramics and polymers, etc. But predominantly you have these three conventional choices of aluminum, titanium, and steel. Now, so what are some of the governing factors here? One is the ultimate tensile strength. Of course, there are regions where compressive strength is more important, but just for simplicity of comparing materials here, we will just look at a particular application where the tension is the more important thing, and therefore we look at just the tensile ultimate strength, which for aluminium is 620 megapascals, titanium 1900 megapascals, steel 4100 megapascals. Again, there are many different aluminium alloys, many different titanium alloys, and many different steel alloys, as you very well know. And so there's a huge range for these. This is just ballpark value for typical aerospace grade materials that are used. So there could be a very wide range. Okay, so you know that even for a single material there is a scatter which is over a small range, but here you're talking of a very wide range of materials. Here we're just talking of ballpark to values to just kind of compare. So don't take these values as a sacrosanct values over there. These are just given to give you an idea of the orders of magnitude difference or the ratios of each of these quantities in a typical case, a typical aluminum alloy, typical titanium alloy, and a typical steel alloy. The next important thing that you have to see, so in the previous case, of course, it's very clear that steel dominates by a very large margin, the ultimate tensile strength of steel compared to either aluminum or even titanium for that matter. So that's quite clear. It's a no-brainer. Now, next, you're familiar with the Young's modulus of aluminum alloys around 70 and steel around 200, 210. So again, you have a threefold fold increase going from aluminum to steel, with once again titanium coming somewhere in between. So tensile strength also, you saw titanium alloys were somewhere in between the aluminum alloys and the steel alloys. Same way with the Young's modulus in tension as well. So it's very important that you qualify these things, because eventually you're going to get into composites which are anisotropic materials. So the reason, even in metals which are isotropic, you see that the behavior in tension and compression is quite different. So this Young's modulus more or less is the same in tension and compression for most metals, but the strength is very different in the tension and compression. Okay, it depends on the granular structures and the microstructures that you have of the metals, how they are the manufacturing process, the heat treatments that they go through. All of this will determine the actual values. But it's important to qualify when you say, let's say, a strength, whether it is in compression or tension, and as we go towards composite, whether it's along the fiber direction or perpendicular to the fiber direction, what we call as longitudinal or transverse. So all these qualifications in a particular material property's name become important. Just saying tensile strength of a composite doesn't make much sense. Similarly, just saying strength of ultimate strength of metal doesn't make any strength, because is it under tension, compression, or shear? So you have to qualify these quantities and become more precise in your wordings of whether you're orally talking or you're having a written document. You should be very clear and crisp in the particular property that you're mentioning. Same thing with the Young's modulus as well, though for the metals it may not make too much of a difference. Next, we come to, and also notice this important difference. The units are megapascals for the ultimate tensile strength, and for most strengths we typically use that, and gigapascals, which is 1,000 times that for the Young's modulus. So that is understandable, because the strain is, the failure strain is typically the ratio of this ballpark values. Of course, we'll go into the exact things later. But if it's a linear distribution, let us say, till the failure, which it is not in the case of metals because of the ductile behavior. You know that the stress strain curve is not entirely straight, unlike for brittle materials where it could fracture in the linear regime itself. But the idea is that the Young's modulus will always be much larger quantity compared to the strengths, because the strain at which it fails is typically of the order of a few percentage, let's say 2%, 3%, etc. It could vary again between material to material, but you're basically looking at such a small strain at which it is failing, which means that sigma u is in megapascals, whereas E is in gigapascals. So make this distinction. So just don't compare those numbers, though both of them are dimensionally the same, because they both relate to stress in some way, and therefore there's a force per unit area that is involved in both. So this distinction in the scale of these values is something that you should recognize. You should get a feel for these numbers. It's very important to, even if not the absolute numbers, at least the relative numbers in terms of how sigma u relates to E, how steel relates to aluminium, etc. The fact that steel is 3 times stiffer than aluminium, it could be about 8 times as strong as aluminium. These ballpark values, if you register in your mind, it makes certain decisions much easier. It's not that this information is not available. It's at the click of your button in today's internet searches. But still, when you have these things at the back of your mind, design decisions become much more faster, and you can proceed, at least in a ballpark sense. Then you go into more detailed design of choosing which particular steel alloy or which particular aluminum alloy. There, obviously, you have to look into the data that is available and the current state of the art, etc. But overall choices many a times are made based on these ideas that you have about different materials. Of course, these ideas can change over time as materials develop, etc. But more or less, some of these conventional materials, there's not too much of a change, not an order of magnitude change that's going to happen. So it's very clear that the ultimate tensile strength of steel is much larger than that of aluminium and titanium as well, to some extent. And similarly, the Young's modulus, again, we're talking about the longitudinal tensile directions. The steel is larger compared to that of aluminium and titanium. So this being the case, it's very clear between just these three material choices that we have: aluminium alloys, titanium alloys, and steel alloys. Steel is the strongest and stiffest. But why isn't steel preferred always?
Because of high density.
Very good, yeah.
Specific stiffness is less.
Steel stiffness is less?
It's very heavy. You have to use it in an area.
Yeah, very good, yeah. So if you...
Specific strength is less.
Very good, yeah. So what we need to really look at are not these absolute values of strength and stiffness, as we very briefly exposed ourselves to in one of the initial classes, but more importantly, we are talking about the specific strength and stiffness, which is kind of weighted over by the densities, because mass plays a critical role in aerospace designs. So that's what we get into. So again, take these three choices that we have: conventional materials, aluminum alloys, titanium alloys, and steel. Now you look at the densities in kilograms per meter cube, SI units. So you look at aluminium is of the order of 2,700 kilograms per meter cube, and steel is all the way up at 7,700 kilogram per meter cube, almost 3 times, 3 times. So you are looking at that, and once again, just like for strength and stiffness, the density of titanium is also somewhere in between these two, aluminium and steel. Of course, it has other attractive properties like high temperature applications, possibility, etc. But it has disadvantages also, that it's much costlier compared to either of these, mostly because there are certain steels and aluminum alloys which could be fairly expensive too. But on an average, you look at huge cost involved. But for higher temperature applications where aluminum and steel may not be useful enough, you have to go for the titanium. But so this is what you answered correctly, that yes, in terms of advantages, steel seems to be good from an absolute point of view, but once you factor in the weight caused by larger density, material density, you have the steel having a disadvantage over there. So still, steel is not always preferred, because if you design a component based only on steel, let's say entire wing made out of steel, you're going to have a far heavier wing, and that's going to make either flight impossible or very inefficient. It's going to fly very slow, or it's going to take passengers, very few passengers for a very small distance, etc. So hence, in a weight sensitive design, which flight vehicle structures and to some extent all moving structures are, whether it's a high performance automobile like the racing cars, etc., or even ships, or trains, buses, or other automobiles, you see that as we go forward into higher and higher performance regimes, and also in terms of the fuel consumptions and the emission levels, you know that there are these emission standards which are enhanced year after year by various standards in various nations or regions like Europe or India, the North American region, etc. And those restrictions in terms of how much of emissions you can have will in turn dictate how much of weight you can have, weight penalties that you can have. So the weight reduction is not only good from increasing the performance, but also from reducing the fuel consumption, and therefore the emissions, and therefore indirectly the noise as well. Okay, so these are all kind of intricately connected things, though we see just an acoustic engineer dealing with noise, the propulsion engineer or the fuel chemistry person dealing with the fuels, etc., or the engine design, etc. But all of these are kind of intricately related, and you should give thought to that bigger picture before you make many of these important decisions. So weight sensitive design, compromise has to be made always between conflicting characteristics. In this case, it's a need to compare material performances, not in an absolute sense, but in a specific sense for various structural applications that we might be interested in. So there are three primary categories of the design situations that we have, which we'll look at. These may not be the only ones. There are various other factors which come in. I briefly mentioned, for example, the impact, the corrosion, the fatigue, and various other, the durability, etc. All these come into picture. But keeping all those aside for now, because they also have a huge impact on the costs that are involved. So they're not something which are negligible, but the most important criteria, primary criteria, at least in a conceptual stage, is these three: the strength, stiffness, and stability. And the reason why I brought that quick quiz also is because that stability is an important criteria for material selection. So even though buckling is a chapter that, or elastic stability, air elastic instability is something that we'll study much later in detail, unless and until you understand that, you will not appreciate the choice of material based on stability, and that can be the critical choice over and beyond the specific strength and specific stiffness. The specific stability might be a critical choice for many of the components, and that's why I wanted you to understand which of these structures undergo compression, because that's where, at least in a different direction from where the actual load is applied, so that you ensure that both global buckling and local buckling are either avoided, or it is still able to operate beyond the buckling, what is the post-buckling regime. So next, we will look at certain actual quantifying these performance indices based on very simple examples that we will take of those loading based components that we took up in the previous class and we revised at the early stage of this class. So we will look at deriving the performance indices for these, what we call as the 3 S's, which are basically your strength, stiffness, and stability, all starting with S, and therefore these are the 3 criteria that you would have, and for each of them we will talk about a material performance index. And now these derivations will not be done in an entire thorough way, because we will take certain things for granted which we will revisit later, but here it's the only purpose is to identify what is that criteria of a particular material property, which you already mentioned. Of course, you know the result. It's for example, for the strength it is sigma u by rho, or for stiffness it is E by rho, but with a slight twist that I shall introduce later in today's class. But stability, you still don't know that particular quantity. But nonetheless, how this derivation comes forth from a very simple analysis based on certain formula, that textbook like formula that you may or may not remember from your undergrad courses, but taking that as the starting point, we will derive the material performance indices for each of these. Let's start with the first S, which is the strength. So strength-based design. So to take an example of that, let's take a beam that is shown over here. It could be a plate also, whatever it is. So we are introducing a particular coordinate system along the length L, which is dominant. Let's say introduce the coordinate system x1, and we will introduce the unit vector b1. These are certain conventions I'm introducing upfront, though it is not necessary for this particular derivation. These are things that we will use often in the class going forward. So I showed that in some of the sketches today as well. So we will consistently use this so that you are kind of familiar with what we are doing here. So we will use bold letters, whether it is typed or in the PowerPoint slides. Bold letters typically mean it's a vector. Okay, so B1 is a unit vector which is along the x1 direction. Similarly, B2 and B3 are along the x2 and x3 direction. In general, you will have a twist, which is basically a wash in or a wash out in the case of an aircraft wing, and a helicopter rotor blade also has an initial twist. So therefore, these unit vectors B2 and B3, which are along the width of this beam and along the thickness of the beam, can in general be functions of x1. That is, as you go along the length of this beam, you can have these B2 and B3 changing their direction. They are unit vectors, so obviously their magnitude doesn't change. It still remains unity, right? But when you say a vector is a function of certain things, even if its direction changes, either its magnitude or direction or both change, then it becomes a function of a particular quantity with respect to which it changes. So in this case, it could be a function of x1. It's not important for this particular example, but so these are things that I want you to kind of remember. So length will usually denote by L, whether it's the length of a panel or length of a beam. We'll typically denote it by L, and then the breadth we will denote it by B, and the height we will denote it by H. So the height happens to be the thickness in most situations, depending upon how you're orienting it. So the H is height or thickness, B is the breadth or the width, and L is the length. And I guess I've explained all those symbols there. So now coming back to the strength-based design, here the criteria based on which you select the material is the failure of the material. So you want to avoid the failure of that material. You want to either avoid or delay that beyond the loads that are known to occur on that particular structure, along with a certain margin or factor of safety. These two are different terms. We'll come to their specific meanings later, but basically you're designing it in a way that it is safer than what the actual material indicates, so that you're operating within the failure envelopes. Next, so for this example, we are considering this particular sheet. As soon as I say it's a beam, what it means is L is very large compared to B and H. If I say it's a sheet, then it means that L and B, that is the length and the breadth, are very large compared to the height or the thickness, right? So as soon as I say it's a sheet, whether it's under tension or whatever, as soon as I say it's a sheet or a shell or a plate, etc., it becomes very clear that it's almost a two-dimensional structure. Maybe if I dimensionally reduce it in an appropriate way, instead of using a computationally expensive 3D model, I can use a very computationally very efficient 2D model. So that so the requirement for that is that L and B are very large compared to H. So this is a statics problem that we're talking about here. So we actually take the geometric length and the breadth, but if it's a dynamic problem, let's say it's vibrating, then the length that you have to take is not the actual geometric length of that sheet, but the dominant mode's wavelength. So in other words, if this is vibrating, let's say sinusoidally, let's say, then which of those modes are dominant, which amplitudes are very large, because it can vibrate in multiple modes, okay? So each mode will have its own natural frequency and mode shape. So from those mode shapes, you will arrive at what is known as a wavelength, okay? So that characteristic wavelength of the dominant modes is what you have to compare with. So in an actual structure, for example, this B and H might be, L and B might be very large compared to H, but still you may not be able to use a 2D model or a plate shell model, because even though geometrically for that sheet L and B are very large compared to H, the dominant wavelength along the L direction, along the B direction, may not be very large compared to H, okay? Because it's let's say a higher frequency mode is dominating, then you have very short wavelengths, and that wavelength of deformation along L might be comparable with H or not very large compared to H, and therefore you might still have to go for a 3D model. So don't just be fooled by the looks of the of the structure, how it is sized. It's also the kind of loading environment it is in. So keeping all that, all those complications aside for now it's a statics problem. All that I need to compare and see is that for a sheet, you know that H should be small compared to B and L. Now what happens? Let's subject it to tension. So suppose it's under tension, and let's say you have the advantage of the Saint Venant's principle that many of you might remember, but nonetheless we will revisit it in one of the later classes. All that it says is that if I apply a tensile load along the x1 direction as an example, so that tensile load, the way I apply on this face that is at x1 equal to 0, and on this phase at x1 equal to L. On these two phases, I can apply it as a concentrated load like this, or I can distribute it throughout the cross section, either in a uniform way or in some particular functional way or in some arbitrary random way. But irrespective of what it is, if I integrate that distribution and get the same value as the concentrated force that I'm applying, yes, the behavior in this region will be different depending upon how I apply that load. But as long as the resultants of those two ways or multiple ways of applying these loads are the resultants are the same, therefore at an interior location, the behavior is always going to be the same. So right now we are not bothered about what is happening at the edges where the loads are actually applied. So the actual load distribution has to be taken into account, and therefore a 3D model is almost essential. But as we move towards the interior regions, far away from the point of application of the loads, you would see that the actual distribution of the load doesn't matter anymore. It's only the resultants of those loads which matter. So let's assume there is a tensile load acting on this phase, and if let's say this is clamped, then that is resisted by the support in the opposite direction here, or it could be a free beam like this, in which a free sheet like this, in which there is a concentrated load over there or a distributed load, the integration of which over that cross section gives the same value as the load that you're applying over here. So basically in the interior location, we can assume a uniform stress distribution, and this is guaranteed by your Saint Venant's principle, which says that if you move interior by an order of magnitude of the order of the cross-sectional dimensions, then you could be safely assuming that the distribution is as good as any other equivalent resultant distribution. So because of this tension that is applied T or P, let us say, you would have that divided by the cross-sectional area, which is a constant throughout in this particular example. The cross-sectional area is just the breadth B times the height H, which is BH. So that load that you're applying divided by BH gives the uniform stress distribution anywhere in the interior. So now, therefore, we can determine this total load carrying capacity. Now, we put aside all other possibilities of failure, if at all they happen to be. In this case, it's a tension, pure tension. I didn't give this as one of the candidate choices because it would have been obvious no. If it's a pure tension situation, the no other loads are applied in this structure, whether it's a beam or axial bar or a sheet, it's not going to undergo elastic instabilities, right? Like buckling. Now, here the load carrying capacity, therefore, is going to be determined entirely by the material failure, as one of you pointed out, even in the case of the bending, where the bending related material failure might occur even before the buckling occurs. Here there's no chance of buckling at all occurring, and therefore it has to be through a material failure which is going to occur. And so the maximum load P that you can apply at this end, if this is clamped, for example, that concentrated load P that you can apply is going to be given by the cross-sectional area into the ultimate tensile strength of that material, because once that stress is reached, it is going to fail. But of course, in reality, it will fail at a much lower load, because there can be local effects which are happening here, and failure might happen in the edges even before the failure happens at the interior. And also it depends on exactly how the this end is attached or supported, the boundary condition at that end. Ideally we say a fixed end, but in reality, how is that fixed end actually executed? For example, we say the wing is like a cantilever, which means that the attachment of the wing to the fuselage, let's say the fuselage is over here and this is the wing, so then the attachment is supposed to be almost rigid. That is what a fixed end basically means. But yes, you do provide very large bulkheads over there in order to attach the wing to the fuselage, and you design it appropriately with the appropriate materials and large enough size of the thickness, etc., to take care of that load transfer from the wing to the fuselage. But nonetheless, it is not exactly a rigid support. Okay, there is a certain level of flexibility associated with it as well. So if you want more precise calculations, for more detailed design or for a damage analysis or for accident analysis, etc., in those cases you will have to revisit that idealized boundary condition of fixed, etc. So, but nonetheless, this is just to derive a particular criteria for material selection alone. So we're not complicating it. But at the same time, at each stage, when I'm talking about a particular thing that I'm introducing, I'm also trying to give you a flavor of the complexities which could be associated with it, so that you don't take it oversimplistically. Though for making certain preliminary decisions, these simplistic things that we are talking about now will be valid. So now let's look at the total structural mass. Very easy to see. It's like a cuboid structure. So the volume is just going to be given by length into breadth into height, LBH, multiplied by the density of that material. So that's going to be, let's call it big M. We'll reserve the small m in many cases for the mass per unit length or mass per unit area, etc. So let's call it as M for this particular component, is given by this. Now, from these two equations, we can eliminate a particular quantity. The quantity that I want to eliminate is also a design parameter. So, see, material choice is one of the design parameters. Similarly, the structural geometry in terms of the shaping and sizing is also our prerogative. So by making a particular choice in the material, I have a different choice that I make for a geometry. So based on that, since the strength-based design criteria now we are trying to derive is purely for the material, I want to eliminate the other design parameter that I have, and which for me is predominantly the thickness, because the length and the width might already be dictated by the chord and the span that the aerodynamicist is giving me. So he needs a particular wing loading to be able to take that kind of generate that kind of a lift to carry that weight of the aircraft and perform certain maneuvers at different load factors, etc. So the overall sizing L and B might already be determined, but I still have a play around H. How much of thickness of material? So first the choice of material, and then how much of thickness I can take of that material. Now I'm not bothered about the thickness of the material because that's a geometric parameter. I'm only trying to have a criteria to choose the material that I want to go. So I will eliminate H from these two equations, equation 1 and 2. I will get rid of the H, and therefore I get the P max. Now I substitute for H as M by rho BL in the first equation, and therefore I get the P max purely in terms of a material parameter and in terms of basically something that I probably do not have a design choice, because this is the mass per unit length. So the length or the span of the wing, for example, is decided by the aerodynamicist, and the mass that is allowed. You saw those histograms that I showed, three-dimensional histograms in the previous case. What is the structural weight as a percentage of the overall aircraft weight that is allowed for the structural engineer to play around with various materials and various sizings. So the overall mass that I can have is also kind of limited. There's an upper limit on that. Of course, if I can give it at a lower mass than that, everybody will be happy. All the other groups, aerodynamics group, propulsion group, the controls group, will all be happy because their job is a little simpler if I can do it at a lower mass than what they are allowing me to. But the upper limit is fixed. So in that sense, I have a cap over these things, and so the pure quantity which dictates the material choice is obviously the specific strength, what we call as sigma u by rho, the ultimate tensile strength by rho, because in this case it was a material which was a structural component which was subjected to pure tensile load. So as I said, it's kind of oversimplifying this whole situation, but this is something which is very, very critical in making a design decision in which material goes in a particular location, especially when it's dominated by tension. And there are many, many components which are dominated by tension, the bottom skin of a wing, the stringers in the bottom, the wing, the spar flanges at the bottom. All of these are predominantly under tension, and so this would be the primary criteria under which the design decisions are going to be made. Next, for a given mass and geometry, therefore, that is M is fixed, therefore given mass, and L is fixed, so therefore for a given geometry. Therefore, the governing factor for having as large a load as possible to be able to be taken, or for a given load having a large enough factor of safety, let us say, you would, to be well within the failure envelope, you would basically be seeing that this maximum load carrying capability is proportional to a material parameter which is sigma u by rho. So in essence, it's a measure of that particular material's performance in strength for this particular case. So that is so any doubts on this, the strength based design criteria deriving this? I think it's a fairly simple and straightforward thing, but if anybody has any questions or doubts on this. Okay, next we go on to the stiffness-based design, and with this we will conclude today's class. The stiffness-based design. Yes, we talked about in an initial class that just dividing the Young's modulus in tension, let us say, divided by the density of the material, mass density, will give you the, instead of an absolute stiffness, it will give you a specific stiffness. We are going to qualify that a little more, because now we are going to bring in a little flavor of the dynamics, okay? Because not all decisions are made based on the static loading or quasi-static loading. There are certain decisions which are actually made by the dynamics that this structure undergoes, the vibrations that it undergoes, etc. Okay, impact is also a time dependent thing. A fatigue is also time dependent quantity. Creep is a time dependent quantity, etc. Instead of introducing all those complications at once, let's look at what the stiffness based design criteria does. The stiffness based design, as you know, anything which is stiff is going to deform much lesser compared to something else which is less stiffer. So basically, if you are interested in dimensional stability as a very important criteria, you should not change the shape and size too much. Then obviously stiffness based design is going to be the governing criteria over and above the strength based criteria. You keep that as a constraint and you try to optimize this. So of course you have to fulfill all of them simultaneously, but which is the dominant one in terms of decision making will depend upon the particular application of the structure. So some structures, the dimensional stability might be more important than the material failure. Some material failure might be more important governing factor than the stiffness based design, etc. So priority levels might change, but nonetheless all of them have to be eventually fulfilled. So the purpose of a stiffness-based design is twofold. One, as I said already, is in a statics problem. It's predominantly the deformations. You want to limit the deformations below a certain level. So you want to keep the deformations as low as possible. So this downward arrow, most of the time I will either use it to say reducing or for very low values, or trying to bring something to the minimum possible that is available with the choices that we make. Similarly, if we go to dynamics, we want to move the natural frequencies farther away so that they're not coinciding with the natural frequencies of some of the components that are there, or the loading frequencies that are there, so that it doesn't go into a resonance and uncontrollable vibrations, for example. So you want to move up the natural frequencies many a times, and once again a stiffness based design essentially leads us to that. And in fact, you would see that these two are very, very closely related to it, as you shall see at the end of this slide, the result that we get at the end of this slide. To just give you a different example, because I just want to bring in a flavor of the different kinds of constructions also. As I'm introducing the material selection and the criteria for those material selection, I'm also introducing various other concepts in a qualitative sense, which will make it easier for us as to understand various concepts as we go forward. In the previous example, I just took a sheet metal, so which is or sheet metal or a sheet composite, doesn't matter, but basically something which is kind of uniform. Now we are talking about a 3-layered structure, a sandwich construction, which has a face sheet on the top, a face sheet in the bottom, and a core in between. That core could be either in the form of, let's say, a honeycomb structure, which is also, let's say, made out of metals of composite, but it could also be a foam. And the face sheets are typically much stiffer or stronger materials, which are much thinner. So you see that actually there are 3 layers over here. The top layer is very thin, the bottom layer is also very thin, and in between you see that those lines that you see, that's basically indicating the core, which can, as I said, either be a honeycomb kind of construction or a foam kind of a construction. Once again, I'm using the same notations to bring in that consistency in all of our classes. So the length is going to be denoted by L, and the breadth is going to be denoted by B, and the overall thickness of course is there, but now that overall thickness is going to be redistributed between the thickness of the face sheets, 2 face sheets that is, and the core. So it's very clear from the words itself you can understand the meaning. Face sheet, it's because that's what is facing the outside and facing the inside, so that's why we call that as the face sheet, and we call it a sheet because it's very thin compared to its other dimensions B and L. And similarly we call it the core because it's basically inside. In an actual sandwich that you eat also, the core is basically what you stuff into in between the 2 breads. So that is basically the core, which is the main nutrition that is there. So that's basically giving you more of the thickness, but in this case you would see that is having much lesser material performance indices like strength and stiffness compared to that other 2, but it's primarily introduced because it has a much lower density. So in the sense that it's not going to give a much of a weight penalty in regions where it is not needed much, because the load that we are going to apply now is a pure bending. So it's once again a cantilever construction like in the previous example. So you fix one end, the other end is free, but you apply a load at the free end, which is a pure moment, which is not a torsional moment, but a bending moment, as you see over here, which is basically putting the top face sheet under tension and the bottom face sheet under compression. So you know that this bending is going to be resisted at any interior point. Again, St. Venant's principle will be taken advantage of. We will not talk about this edge. We will not talk about this edge of the order of the thickness or B. So we will be talking about the interior region where it's a pure moment which is distributed, and therefore you have the top sheet undergoing tension, the bottom sheet undergoing compression, the core not taking much of that bending load because it's not capable of, and it's primarily taking, in the case of, let's say, if you had instead of a bending moment or a pure moment you had a transverse load, then that shear coming from the transverse shear coming from that will be predominantly taken by this, because you know that the bending stress has a linear distribution going from large tension on the top to large compression in the bottom, in between going through 0, which is basically what we call as the neutral axis of the beam. So that particular neutral axis, on the other hand, is going to take the maximum load if there was a vertical force over here, let us say, which is there in the case of a wing, for example, in a lift distribution. So that is going to cause a transverse shear, and that is not going to be resisted by the face sheets much. It's mostly the core, whether it is honeycomb or the foam, that is going to resist that. You know that there's a parabolic distribution of that shear stress. We'll go into all those details later. But coming back, there's no transverse load here, only a pure moment. So in this case, let us say it's a cantilevered, thin-walled sandwich beam. The face plate's thickness we will denote by T. So there is a small t thickness on the top, small t thickness in the bottom, along with the core. Total thickness of that 2T plus the core thickness is equal to H, which is the total thickness. So T is not only is let us say the B and the T small small compared to L, but the thickness of the phase sheet is also small compared to H. So there are certain small parameters which are arising from the geometry that we need to have an eye for, because it is these small parameters which will help us to do the dimensional reduction in an appropriate way, because we have always been saying 3D modeling is very good, accurate, but it's going to take a lot of computational resources in terms of time and cost. So therefore, we need to go wherever it is possible, we'll go for a 2D or 1D model, which means dimensional reduction. So for that dimensional reduction to be accurate enough, we have to take advantage of these small parameters, not only the cross-sectional size small compared to the length or the thickness small compared to the length, but within a cross-section, there are certain things which are happening. So that has to be taken into account as well. And there could be certain material properties. We just now discussed that the stiffness of the core will be very small compared to the stiffness of the phase sheet. So that ratio can be used as a small parameter as well. So when we say dimensional reduction, it's not necessarily 3D spatial dimension to a 2D spatial dimension or 1D spatial dimension. We are talking of a mathematical algorithm here. It's an n-dimensional space that we are operating in. These n dimensions are not all spatial dimensions. They have 3 spatial dimensions, but there are also many other design parameters. All of those constitute a particular field in which we are operating, a domain in which we are operating, and we have to make the design choices. So when we are doing something like that, a dimensional reduction could be some of those design parameters not playing a significant role at all and therefore going away. So just like when we are going from a 3D model to a 2D plate model, all we are saying is that the thickness dimension does not play a big role. We can just analyze along the surface. So that's the design decision. Similarly, some other design parameter, like let's say the core stiffness, may not play a big role here in the pure bending problem. So how that gets eliminated is also in essence a dimensional reduction in a mathematically algorithmic sense, may not be in a spatial sense. So just keep all of these at the back of your mind, because this will help us when we say we want to go for more and more reliable dimensional reduction methodologies. The second aspect is that the mass and the stiffness of the core are very, very small because it has a very low density and it has a low structural performance in terms of stiffness as well. But it's not of much significance there. It's just to fill that space and maintain the form. And of course, when there is a transverse load, to take the transverse shear as well, which is not the case here. So now the moment of inertia, because the core is not going to anyway contribute much, is the moment of inertia about the neutral axis, which is basically the mid plane of this sandwich, is going to be given by 2 times the area of cross section of each of the phase sheet. Because there are 2 phase sheets, we have put this factor 2. Now the cross-sectional area of the phase sheet is given by its breadth into the thickness T, which is the faceplate thickness. So B into T is the area multiplied by the distance at which they are. Even though the total distance is H, because H is very large compared to T, I do not need to say H by 2 minus T by 2 or whatever, right? So I can, because that difference is not going to be very different from H by 2 itself. So I take the distance of that center of this from the center of the phase sheets from the neutral axis or neutral plane to be H by 2. So that H by 2 squared multiplied by the cross-sectional area multiplied by the number of phase sheets gives you the total moment of inertia for this case. Then going to the mass per unit span. The mass per unit span is going to once again be very easy. It's just going to be, in the previous example, we just multiplied by the density by the total volume. Here we are going to multiply only by the cross-sectional area, not by the length. So if you leave out the length, the only thing that is there, and because the mass of the core is very small, because its density is very small, we can ignore that, and the total mass can be thought of as just the mass of the phase sheets. So therefore, it becomes again 2 phase sheets, the density of the phase sheet material multiplied by the B and T, which is the breadth and the thickness of the phase sheet, each phase sheet. So that's the cross-sectional area of each phase sheet. So that gives you the mass per unit span or unit length of this beam. Next, the first bending natural frequency. This I'm going to give without the actual derivation there, but you can very easily see that the correspondence between this and let's say the Euler buckling formula, or in this case, let's say the natural frequency associated with a spring mass system, let's say square root of K by M, which is for a single degree of freedom system with a spring stiffness, linear spring stiffness of K, and a mass which is hung over that of mass M. We know that the natural frequency is related to square root of K by M. So similarly, you see the square root here, power 0.5 of the bending stiffness divided by the mass per unit length. So that is the kind of factor that is there. Of course, the length is also going to affect it, how long it is. So 1 by L squared, and again, it's not equal to, but it's proportional to this particular quantity. But I just I'm giving this without a derivation, primarily to get the stiffness-based design criteria. We will revisit this when we go into the structural dynamics, either in this course or in the other courses that you might take. So the end effect is that I want to now eliminate this mass per unit length of this, and therefore I get it in terms of h by L squared into E by rho power 0.5. Remember, in the previous case I did a different thing. I eliminated the mass because the thickness that is there, because that is the design decision making parameter. In this case, I'm eliminating the mass because I want to see two different design parameters, how it depends upon. I want to have a control over both. One is over the material, I want to have a control. The other is over the geometry. L again, I might not have control over because the aerodynamicist dictates that, but H I have control over. So something which I can't do by this, can I do it by changing the thickness? So that's basically the reason why here we are now eliminating the mass, and also because you can think of the mass as because now we're talking of the almost the overall mass that we are talking about, because the core mass is negligible, and therefore this is the structural weight percentage which is allotted to us for the wing design, and therefore we have to operate on a particular maximum limit over there. So from either of these perspectives, we are, from these two equations, we are eliminating M and saying that the natural frequency, the first natural frequency in bending, because there are many other natural frequencies associated with this structure, is basically proportional to two quantities. One is a geometric quantity and the other is basically a material quantity. Now within this, you see that what we had talked about earlier from a statics deformation point of view, that E by rho is very important. Even though you might have very large absolute values of E for steel, we still didn't choose it because E by rho may not be substantially better than let's say aluminium or titanium. So that's the reason why we went ahead and chose aluminium alloy for many of our aircrafts in the previous century. So now let's see a new thing that has arisen here because of the dynamics that we brought into picture, the natural frequency. Therefore, it's the square root of E by rho which is going to be a predominantly important factor over here, and so that's what we will see going forward. So for a given geometry, the natural frequency in the first bending, which is the most important for many specific applications and many components, then you have to look at E by rho per half, that is the square root of E by rho, as the material performance index for the stiffness-based design. So I'll end the class with this. If there are any questions either on this slide or the previous ones, I'd be happy to answer now.
Sir, this is Amanvay.
Yes, sir.
Sir, the first point in the purpose, sir, I understood that in statics deformation, we want less deformation. Mm-hmm. So what do you mean by the second point? We want a very high natural frequencies.
Yeah. So what this essentially means is that you're shifting the natural frequencies away from the typical loading frequencies, because you know the typical kinds of loads, what kind of mechanical frequencies they would excite. Okay, this is the loading, the external exciting frequencies. So you want to keep your natural frequencies away from that. So you're trying to move beyond that because
okay.
Because the loading frequency might slowly build up, and it might go through that natural frequency of that particular structure if it is very low. So we just push that away to a higher level, so that as the load's natural frequency increases, the load's frequency increases, exciting frequency, it will not cross the natural frequency because the natural frequency is even higher. So that is the whole idea of pushing the natural frequencies beyond a certain level.
For the resonance purpose, sir. Because
Exactly.
if they match, then resonance will
Absolutely.
not. Okay.
Yeah.
Okay, thank you, sir.
Yeah. You're welcome.
Hello, sir.
Yes.
I have one question.
Yeah. Please go ahead.
Sir, I have one question. Whether this E by rho will be for metal, all metal, it will be same, more or less, it will be same only, no?
Yeah, exactly. So we will look at those actual numerical values as we go forward. What you're saying is right. So if it's purely based on a stiffness-based design, you may not have much of a choice between the materials. So you might choose whichever is cheaper or whichever is more readily available to you, or which is able to handle other things like corrosion, etc. better. So that's what your choices will be dependent upon. But as I said, this is stiffness-based design is only one of the criteria. We already looked at the strength-based design, and we are in the next class, the beginning of next class, we are going to look at the stability-based design. So there you will see that the three materials that we already looked at, the metals, aluminum alloys, steel alloys, and titanium alloys, will behave very differently for a stability-based design. Whereas for a stiffness-based design, what you pointed out is absolutely right. The E by rho and therefore square root of E by rho also will be approximately the same for all those three materials.
Hello, sir. This is Ashish.
Yes, please go ahead, Subhashish.
Sir, can you explain that's in terms of masses?
Subhashish, can you speak closer to the microphone or a little louder so that I can hear you?
Sir, can you explain? Sir, I think someone else is talking.
Okay. Go ahead. Whoever it is, just come closer to the microphone and talk louder because it's very low volume.
Sir, can you explain more in terms of mass and stiffness that you mentioned in everything what said yesterday?
Did anybody else hear the question? You can repeat it for me. Hello.
Hello, sir.
Maybe you can type it on the chat so somebody, Vignesh or one of the teaching assistants can read it out. Yeah, in the meantime, Subhashish, you can go ahead with your question.
Yes, sir. Sir, you mentioned that in this dynamic situation, we want our natural frequencies to be high, so that the exciting frequencies does not match with the natural frequency of the structure.
Yeah.
But there might be situations like where the operating the forcing frequencies are already in the higher ends.
So there it doesn't matter. So this particular criteria doesn't matter, but still you would want to keep your deformations low, and therefore for that also E by rho becomes a governing factor. You may not be comparing the square root of E by rho, but E by rho. See, whether you compare square root of E by rho or E by rho, the decision is going to be the same, but by what margin is going to be different. So the square roots of E by rho might be much closer to each other for two materials compared to the E by rho itself. So which is the more important governing decision? So are you able to make a certain small sacrifice even though the square root of E by rho is slightly smaller for a particular material, but that material could be the material of choice based on some other considerations. So then you would still go for that. So whether it is statics or dynamics, the choice of that particular thing depends upon, that is whether the performance index is E by rho or square root of E by rho, depends upon whether dynamics is important for that particular component. If it's not going to be anyway subjected to much of dynamic loads, and or as you said already, it's known that the loading or exciting frequencies are going to be at much larger values, so then you might still want to keep it low. If you increase it, you might actually go closer to that exciting frequency. So you really don't want to do that. The whole idea is to avoid that, and you know that most of these exciting frequencies which come, let's say, from a gust, or it comes from various other loads that you have on the aircraft are typically of the lower range compared to many of the natural frequencies you have for structures, and which is why we are trying to say we push that forward. But there can be exceptional cases like what you're talking about where that may not be the case, but still based on the other consideration that you want to keep the deformations low, you would still want to keep a low as high a E by rho as is permissible. Yeah.
Got it, sir.
Okay, welcome. The other person's question, could anybody read out from the chat if he has already sent it? I'm still not able to hear clearly. Have you typed it on the chat?
Yes, sir.
Okay, so can you throw some light on the core in terms of mass and stiffness? That's what you asked, right? Yeah, okay. So let's go back to that. The core is basically what is in between the two phase sheets, right? So as I said, it is basically made either out of a honeycomb or a foam. Okay, so now obviously these kind of structures are having overall density, mass per unit volume, if you take the spacing between the honeycombs as well, much lower, even though it might be made of the same, the honeycomb might be made of, let's say, the same material as the phase sheet, but because there is so much of void or gaps in the honeycomb structure, the overall density of that region occupied by the core is much smaller. So that therefore, even though it is much thicker compared to the phase sheets, because the density is so much smaller, you are going to have much lesser weight penalty coming from the core. So that's basically the reason why in the previous example, the derivation, we ignored the mass of that. Similarly, in terms of the stiffness contribution of that in the moment of inertia, because for the bending stiffness EI, we need the moment of inertia I, and for that I also we took only the phase sheets because this is having such a low value of Young's modulus compared to the phase sheets. The core is having a much lower Young's modulus, and therefore it does not, it hardly contributes. The other thing, of course, is it's a pure bending, and you know that the bending stress distribution is linear with the neutral axis or neutral plane being here. And therefore, on the neutral plane, there is anyway not going to be any stress. So this is an unstressed region or very lowly stressed region, and therefore it's not going to take any of the bending load by reacting with its stress. So almost all of the stress is going to come from this phase sheets. So if there is a moment like this is reacting with a tension because it's under compression, it's basically reacting with a force in this direction, and this is reacting with a force in this direction, so that it's kind of counteracting the moment, and therefore you see that we can ignore the mass as well as the stiffness of the core. Does that answer your question?
Yes, sir.
Okay, thanks, Ashish. Anybody else? Okay then, thank you very much. We'll meet on Thursday and we'll take forward the third material performance design criteria, the third S amongst the three S's that we talked about, namely the stability criteria. Thank you. Have a great week ahead.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome.
Thank you, sir.
See you. Bye-bye.
Thank you, sir.
Welcome.
मृत्युंजय मंत्राः
त्र्यंबकं यजामहे सुगंधिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् ये ते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा